Unfortunately, in our system of government, the vice president is like the Queen of England. You can't even get airline tickets without talking to somebody like me.
In this video, we're going to continue our study of angles formed inside of a circle. One type of angle we've already looked at are central angles, which basically are exactly equal to their intercepted arc, meaning that the measure of this angle 1 is equal to the degree measure of the arc which it intercepts, in this case AB, just depicted here. The measure of angle 1 is equal to the measure of its intercepted arc. Two other kinds of angle relationships we're going to look at are those formed by intersecting chords and those formed by what are called inscribed angles. Now, an inscribed angle of a circle is an angle whose vertex is on the circle and whose sides are made up of chords. So unlike a central angle whose vertex is at the center, an inscribed angle is one whose vertex is on the circle and its sides are made up of two chords of that circle. Okay, so let me label this. I'll call this angle ABC. Okay, so this is angle ABC with vertex B is an inscribed angle. It has its vertex on the circle. Now, there's actually a relationship between its intercepted arc, which in this case is AC, this arc, and the measure of angle ABC, this angle right here. Okay, and that relationship turns out to be that the measure of an inscribed angle is equal to 1/2 the measure of its intercepted arc. What that means is the measure of this angle in ABC is going to equal 1/2 the measure of arc AC. So here's a couple of examples of that. In this case, I have three values of x. For the first one, the measure of the arc is 74 degrees. That means that the measure of the inscribed angle of that arc, x, would be half of 74. So x is 1/2 the measure of that intercepted arc, telling me that x is 37 degrees. I can do this process in reverse. If the measure of the angle, the inscribed angle, is half the intercepted arc, then vice versa, the arc is double the measure of that inscribed angle. So since this inscribed angle is 42, the arc must be double that length, which is 84, in order for the angle to be half that arc. Sometimes we have to put a couple different angle measures together. Here I have a central angle of 100 degrees, and recall that an arc intercepted by a central angle shares that same angle measure. So this arc is 100 degrees, which means that this inscribed angle, which is half that arc, would be 50 degrees. Okay, so an inscribed angle is always half its intercepted arc. One other thing that we talk about sometimes with inscribed angles are inscribed figures, such as an inscribed triangle. In this example, it says that triangle ABC is inscribed in circle O such that the following relationships are true. Well, an inscribed figure is basically a figure whose vertices all fall on the circle, or whose vertices all form inscribed angles. So if you notice in the diagram, triangle A, B, C, each of the vertices of that triangle form inscribed angles. That's what it means for a figure to be inscribed in a circle. With the rest of the given information, I know that the measure of angle B is 70, which means that the measure of arc AC, the arc which that angle of 70 degrees is inscribed within, would have to be double that, which is 140. I know that arc BC is 100, which means that the the angle inscribed within that arc would have to be half that, which makes it 50 degrees. And then to find the remaining bit, I know that the sum of the angles inside of a triangle are 180, so 70 plus 50 is 120. And if I subtract that 120 from 180, I'll get the missing angle, which is 60 degrees. So this must be 60, which means that the arc which this angle is inscribed in, right here, would need to be double that, which is 120 degrees. One check for ourselves is that we know that the sum of the angles or sum of the arcs within a circle is 360, and if I add 100, 120, and 140 together, I do get 360, so that's a check. So when I go to answer these questions, now that I've solved each of these bits, the measure of AC is 140, the measure of A is 50, the measure of angle C is 60, and the measure of arc AB is 120. Okay. The other type of angles that we look at which are formed within a circle are angles formed by intersecting chords. Now remember, a chord is just a line segment which connects 2 points on a circle. So one chord here would be AB, connecting 2 points on the circle, and another chord here would be chord CD. Now it turns out that the measure of the angle formed between these two chords is equal to the average of the arcs intercepted by the angle and its vertical angle. So what that means is, if I was to look at what the measure of angle AEC is this angle right here. The measure of that angle is equal to the average of the arc it is intercepting and the arc that its vertical angle is intercepting. So I'm going to say the measure of arc AC plus the other one is BD, the measure of arc BD over 2. This angle is the average of those two arcs. Similarly, if I wanted to know what BEC was, BEC is this angle. I'm looking for the measure of this angle. It would be the average of the arc directly across from it and the arc directly across from its vertical angle. So that would be the measure of AD plus the measure of BC all over 2. So let's see a couple of examples of that. First, I tell you that the measure of arc AD is 100 degrees. Now, one thing I recommend when you're doing questions like this is to have either highlighters or colored pencils, because it can help you in highlighting what arcs you're talking about. So I'm going to highlight arc AD, and I'm going to label it 100 degrees. I also know that BC is 68 degrees. And I ask for the measure of angle BEC. So BEC would be this angle, and I'll label that X. Well, the measure of this angle, X, is equal to the average of the arc across from it, which is my 68, and the arc across from its vertical angle. And the angle vertical to X is AED, and the arc across from that is the 100 degrees. So the average of those two values is their sum divided by 2, which gives me 168 divided by 2, which gives me 84 degrees. Scrolling down to my second example, we can also use this process in reverse to solve for missing arcs. So for example, if the measure of arc AC is 56 degrees, AC is this arc, is 56 degrees. And the measure of angle AEC is 80 degrees. I need to find the measure of BD, this arc. So I'll call that X. Well, according to the relationship I've already stated, the measure of an angle, in this case AEC, is equal to the average of the two arcs. The two arcs in this case are 56, and the one across from its vertical angle is X. So I'm going to have to sum up X, the measure of the first arc, and 56, and divide by 2. So the reason that the variable X in this case is showing up on this side of the equation is it's the measure of one of the two arcs. It's always the angle is the average of the arcs. So my two arcs are 56 and X. The average of those two things will equal my angle, which is 80. When I go to solve this equation for X, I'm going to start by multiplying both sides by 2. If I multiply both sides by 2, my 2's will cancel out on this side. That way I don't have to deal with the fraction. 2 times 80 is 160 equals X plus 56. Then I'll just subtract 56. Just a little bit of equation solving so that I get X is equivalent to 160 minus 56, or 104 degrees. Okay. Here we've talked about central angles, we've talked about inscribed angles, which are always half the measure of their intercepted arc, and we've talked about angles formed by intersecting chords, which are basically the average of the two arcs. With these relationships in mind, we can actually find more observations about relationships within circles. For example, if we look at number 3 here, in order to figure out the value for X, what I can do in this situation is actually a clever little construction and make this inscribed angle an inscribed triangle by connecting the other two points on the circle. Now recall that an inscribed angle, namely this angle, is half its intercepted arc, and it's intercepting the 135 degrees. Well, half of 135 is 67.5 degrees. Now, because this is an isosceles triangle, because these two chords are congruent, it means that these two base angles will be congruent to each other, and that this angle will also be 67.5 degrees. Well, if these two angles are both 67.5, notice that my second angle here, I'll actually highlight it in green so that you can see it a little bit more clearly, is also an inscribed angle, which inscribes this arc. Well, if it's 67.5, then this one must be 135 degrees. Well, this is actually a really interesting observation. Notice that these two congruent chords cut congruent arcs in this circle. That's actually a relationship that's always going to be true. Congruent chords will always cut congruent arcs. So since we've made that observation, I'm going to go back and see how we could use that to solve for X in a slightly quicker way. Now that we've observed that, we haven't proved it, but it can be proven mathematically that congruent chords cut congruent arcs. So, since this is 135 and this chord is congruent to this chord, the arc which this chord is cutting from the circle will also be 135 degrees. If this is 135 and this is 135, and the total number of degrees in a circle is 360, we can subtract this, these two 135s from 360, to figure out what the remaining arc would need to be. Well, when we do that subtraction, we end up with 90, meaning that this arc must be 90 degrees, and its opposite inscribed angle is therefore half of that, which is 45. So this little idea, congruent chords cut congruent arcs, is a time saver that can help me in solving any type of equation like this. One other observation that we can make, in the second situation, notice that we have a diameter and a triangle inscribed in that diameter. This inscribed angle is actually cutting this arc of the circle, and because this arc is cut by a diameter, it makes it a semicircle, meaning it's 180 degrees, so that this inscribed angle must be half of that, which is 90. Well, that would mean that any angle inscribed in a semicircle would be 90 degrees, or a right angle. And in fact, that is a relationship that will always be true. An inscribed angle in a semicircle will always be a right angle. And I'll write that right into this diagram. Okay. The last pattern of relationship we can observe is that these two inscribed angles, x and y, are inscribed within the same arc. If I trace x's sides to my arc, I can see that it's cutting the 80-degree arc, meaning that x must be half that, which is 40. And if I do the same with y, I can see that y is cutting that same arc. So y must also be 40. In fact, in general, two inscribed angles of a circle which intercept the same arc will always be congruent or equivalent to each other. Notice that x and y are both 40, therefore x and y are congruent or equivalent. So in this specific situation, x is equal to y. Okay. Well, these three ideas are basically shortcut observations that can save you a lot of time when doing circle questions. Using those ideas and the angle relationships, which we've already talked about, I'd like you to take a look at the 3 remaining questions on your sheet and attempt each of these now. We will go over them in class tomorrow.